Okay, good afternoon, everybody. Let's start the lecture. So there's one-page handout here, okay? Make sure you grab that handout, and we may use that. So in the previous lecture, what we have done is we have considered fatigue failure, okay? And we have created so-called SN diagram. Okay. But in either case, okay, so what we have considered is basically is called completely reversed loading or stress. Okay, so those are the previous lecture what we had considered here. So complete reversed. This is what it means here, right? Yeah. So now, in this lecture, we're going to look at a more general case. Okay. So the general case basically is, what if we have the so-called fluctuating stress or loading? Okay. So what this means is basically the loading, instead of a complete reversed, and we can have this is kind of loading here. So this is what we call fluctuating stress. And this week of tutorial, you have a similar materials in terms of this, some details as what would give you this fluctuating stress. So essentially, it's a sinusoidal curve, which has a mean value, and the mean is not 0 anymore. And it's a sinusoidal curve, so it must have amplitude. And that's sigma A, the amplitude. And it also have the maximum value. It also has this mean value. Okay? So this kind of curve is called fluctuating stress. So essentially, your sigma m it's not 0, and sigma A is not 0. That's fluctuating. And of course, fluctuating kind of stress it's essentially a more general case. See what happens, what if you set sigma m equal to 0? Then you basically have this the completely reversed loading, right? Yeah. So what if you set what if sigma m is not 0, but sigma A is 0? So what does this guy become? Exactly. It just be a line. It's not fatigue anymore. It basically becomes. It's not fatigue. Then it's what? What did we learn before the fatigue? Static, right? Static. So if sigma m not 0, but sigma A is 0, so this is basically a static loading. And if sigma m is 0, but sigma A is not 0, this is a completely reversed kind of loading condition. Okay? Yeah. So for example, if I have a shaft, let's say suppose this is a shaft here. Simply supported. Then the shaft is subjected to a constant force in the middle. At the same time, this is a rotating shaft. So rotating. At the same time, it has a torque. Constant torque added to the shaft. So F and the T are constant. Let's say F and T are constant here. All right. Yeah. And you know what? Actually, I'm jumping ahead of myself a little bit here. So this is actually in the future my combined loading case. I'm not sure I'm talking about this one. Yeah. Okay. Keep this one in mind here. We'll draw this figure a little bit later here. Okay. Yeah. So this is actually combined loading, but so I'm trying to come up with a Okay, let's say erase this t here. Okay, erase this t here. Okay, rotating shaft. Okay, instead of a t, okay, let's say I have a constant p at here. Okay, instead of t, I have a constant tensile force. Okay, yeah. So now if you cut a cross section, okay, anywhere along the shaft. So you look at the cross section, and you look at the stress fluctuation at a certain location on the cross section A, right? So what will be the fluctuation curve look like given the current loading condition at here? Fp are constant, but it's a rotating shaft. So if there's no P here, if I cut a cross section looking at this location A, and it's rotating at the constant speed omega. So basically, the A here will exhibit a what? A complete reversed kind of loading, right? A stress. But now you have the P here. The P will basically add a constant tensile axial loading, basically add a constant tensile stress on it. So this curve will basically move up, right, by a constant value, and that'll give you this so-called fluctuating kind of a loading condition, right? So that basically, and this m value here, it's basically p over a, right? Basically p over a. Okay. So this is a kind of one example that you can have this kind of fluctuating kind of a loading condition. Okay. Yeah. So when it's a fluctuating kind of loading condition, there are a couple of equations, okay, you need to come up with in terms of the relationship here. So what's the relationship between sigma max, sigma mean, and sigma m, and sigma a? So just by looking at the curve there, your sigma m will be max mean over 2. Okay. So this is a very important formula. Okay, you will need this in terms of calculation. And your sigma a will be max minus mean over a. Okay. More precisely, we need an absolute sign in it here. Okay, we need absolute sign. So if you look at this one here, if that makes sense, so it's the max minus the mean, right? Will be the value between the top and the bottom here. And then divided by a, that gives us the amplitude, right? Yeah. So this formula here, right? If sigma m is greater than 0, then you don't need the absolute sign. Okay, then you don't need the absolute sign. So if sigma m is greater than 0, your sigma max is guaranteed to be larger than sigma mean. Okay, yeah. Okay, so this is basically the relationship at here. Okay, and the other relationship you might have is what about expressing sigma m? Sorry, what about expressing sigma max in terms of sigma m and sigma a? Sigma max is what? Plus, right? Plus. Okay, yeah. So this maximum value, often in time, it's what we concern. Okay, this maximum value here. So why this is particular interest? Come again, sorry?
You always design it for the max value. That's what you want.
Design for the max value, exactly. Now, design for the max value, but there's one specifically that you need to use this max is what happens if you're not considering fatigue, you just consider static. So what happens is that if this maximum value is actually become bigger than the yield strength, right? So basically, even if this is a fatigue kind of loading, if the maximum value here is actually bigger than the SY value, then every cycle, the part is actually experiencing yielding. That makes sense? Right? So this maximum value here, often in time, is also our concern here. In the later part of the lecture, you'll see we call that first cycle yielding. You see, even if the one cycle is not finished yet, your maximum value, if the max is exceeding this SY, then you have this so-called first cycle yielding there. Make sense? Yeah. Okay. So this is basically one particular reason that you need to, sometimes you need to consider this one here. You need to look at, is it going to be greater than SYT or not? Okay. Yeah, that's one concern. Okay. So we'll talk about details about this one here. Okay. Yeah. So that's fluctuating kind of a stress here. Okay. Now the natural question is, in previous lecture we were trying to create, if you remember in the previous lecture, we created a SN diagram. So this is the SN diagram that we created, and this axis here is sigma A, and this axis is number of cycle, right? And this SN diagram is created for a completely reversed loading condition. Is that right? Okay. Now the question here is, if I do have a sigma m in presence, okay, so now it's not just sigma a anymore, it's sigma m there. Maybe positive, maybe negative, right? What will be the effect of this sigma m on this SN diagram? So what will be this effect of this sigma m on SN diagram? Okay, on the SN diagram. Well, in other words, before we talk about the effect of this on the SN diagram, so what information does SN diagram tell us? It tells us what will be the this endurance limit, right? And it also tells us at a certain stress, and what will be the corresponding number of cycles it can endure, right? That's basically what SN diagram tells us. So now you introduce the sigma m loading into this loading condition. Suppose that sigma m is less than 0 or sigma m is greater than 0. So that's basically going to be the two kind of situations here. So if sigma m, let's put this way here, if sigma m is less than 0, so sigma m less than 0 basically means, if I draw the diagram, if I draw the curve, so instead of the curve is here, actually the mean value is going to be below here, right? Mean value is going to be below here. So it's more of like a, so the mean value is here. Okay? Mean value is here. So you have a mean value which is less than 0, and this is tensile stress. Basically it's not tensile, it's actually what? Compressive, right? Compressive. So when we learn fatigue loading, and we said there are 3 stages of the process. The second one is the crack propagation, and the crack propagates only under what? Tensile stress. So now you have a less than 0 component introduced into it. So basically the whole thing lowered down itself, right? So in terms of the SN diagram, if I wanted to redraw a SN diagram with a sigma m is less than 0, what do you think? Do you think I'm going to have a bigger fatigue strength, or in other words, am I going to have a longer cycle to fill because of this sigma m, right? So if I redraw it, then it would be a SN diagram. Actually, it will be on the top of this guy here, right? It will be SN diagram on the top of this. Okay, so it will be something like this on the top of this. Okay, and that's when your sigma m is less than 0 here, right? Less than 0. Okay. So consequently, similarly, if sigma m is greater than 0, then you're introducing an additional tensile stress, mean tensile stress, into this loading condition. Right? So it will be something like this. So naturally, what happens is it'll basically reduce the fatigue strength, or it'll reduce the number of cycles for you to fail, right? Because it's under an accentuated tensile stress, right, for the part. Okay, so then the SN diagram, it will be a curve below this guy here. Okay, yeah. Greater than 0. Okay, yeah. So that's essentially, you can see whether it's under compression or it's under a tension here for S sigma m, for the effect of sigma m. Okay. Okay, so that's SN diagram here. Okay, and to understand this. Now, what we're going to deal with mostly, so where we're going to focus, okay, mostly is the sigma m greater than 0. Okay, yeah. So we're going to focus on the sigma m greater than 0 situation. Yeah. The other one is a simple question is, so what if sigma m is greater than SUT? Then what happened? Come again? Exactly. Right. Actually, it's going to basically fracture, right? It's basically will fracture on the first cycle. Okay, that's the effect sigma m. Okay, yeah, so that's another thing here. So if you draw this circle, if you look at this guy here, right, this is the sigma m greater than 0 at the bottom here. If you keep increasing the sigma m, then the bottom SN diagram will basically become a flat line at here. Okay, will become flat line when sigma m is the same as SUT or greater than SUT. Okay, yeah, so it has a first cycle yielding. Okay, so now we understand this effect of sigma m, and what we're more interested is, what we're interested in is what will be the fatigue, okay, fatigue failure theory, okay, for this kind of fluctuating stress. Okay. Yeah. So let's just think about a simple one here. If this is not a fluctuating stress, if this is just a complete reversed stress, what is the fatigue failure theory, or what is the way to calculate safety factor? So if sigma m is 0, how do I calculate safety factor? Come in, sorry.
SUT over stress on alpha.
SUT? Not SUT. SE. Right, SE. Remember this SN diagram here. This is a complete reversed, right? If I'm designing for infinite number of cycles, so you're comparing this SE value with your current state of stress, which is the amplitude of the stress, right? Sigma A. Then if it's less than that, you have an infinite number of cycles. If it's greater than that, you have a finite number of cycles. If you have finite number of cycles, in the previous lecture we had a couple of equations to derive what will be the finite number of cycles to calculate that, right? Okay. Okay, so this is basically the way to calculate this the safety factor if it's completely reversed. So if it is not completely fluctuating, then what do we do is people do this experiment. Okay, yeah. So we need a couple of theories first. So this is one way of doing experiment here. So the way to do experiment is basically it's like this. You set sigma m to a value. Okay, yeah. So you set your sigma m to a value, then you change the amplitude sigma a. Okay, yeah. Then you subject, right? For example, you have a pair of sigma m and sigma a now, right? Okay. Then you subject the part, okay, to this pair of this value at here, and then you observe, how many number of cycles will the part fill. Okay, so you basically collect data based on this kind of process here. For example, if you're interested in infinite number of cycles, okay, so this is what happens. You look at the 10 to the power 6, the value, and at what values here the part will exhibit this 10 to the power 6 number of cycle failure. That makes sense, right? So then you basically plot all of this different situation, different combinations of sigma m and sigma a at here into this diagram. But this diagram is sort of a scaled using they call it SMSA. I'll explain this in here. Okay, so you can, if you change this S to sigma m over S to sigma a over S E here. So that's basically all the dots there. Okay, that's all the dots. So the dots essentially represent it's a pair of this value at which you have this boundary of this 10 to the power 6 of failure there, right? Yeah. So looking at all the dots here, apparently you can use one of this straight line to approximate all this data at here, right? To approximate the data. Okay. In terms of SM, SA, okay, if I to be more specific at here, if later you will see this SMSA here. So what are they? They are more or less like those values. If you remember, there's a so-called SF here, right? SF. So one of the questions asked in the previous lecture is, what's the difference between SF and sigma A? So SF is the value corresponding to any point on the curve. Okay, so if you have a point here, then that's called SF. If you take a value anywhere inside this plane here, and that's called sigma A. Okay, so now looking at this curve, the SMSA, okay, so this SM is called the limiting value, okay, for sigma m, and this is the limiting value for sigma A. Okay, yeah. And sigma m is the mean value, so more precisely, it's the mean strength. Okay. And sigma a is the alternating component. Right? You have this amplitude. That's the amplitude. So this SA here, what we call is alternating. Okay, not the length, mean strength. Alternating strength. Okay, alternating strength. Okay, so more precisely, if you take a point on the curve at here on the straight line here, that corresponding value give you this, it's SA and SM. Okay, yeah. So if I take any point here, here, or here, here, right, and we don't call them SASM, we call them what? Sigma A and sigma M. Was that good? Okay, so if you have a point over here, it will be sigma A and sigma M. Okay, so now you got this diagram in here now, and so the whole question here is, okay, this is one way of approximating this data here, and you can definitely see maybe I can have some other ways to approximate the data here, right? So that's actually the basis of the following failure theory. Okay, so I'm going to draw a new curve here. Okay, I'm going to draw a new curve here, and so we're going to call this a sigma A axis and a sigma M axis. Okay, sigma M axis. Okay, so instead of using a ratio between sigma A over SE and sigma M over SUT, so let's redraw this one here. Okay, so the first diagram, okay, is this. So what you do is, if this is a special value SE, okay, so why is this special value SE here? So suppose your sigma M is 0, and if I wanted to design, basically what do? You compare sigma A with SE, right? So this is why it's a special value here. And we're going to connect, if you look at this one here, this guy here, what's the special point? This is the ratio between SM and SUT equal to 1, right? To 1, which means what? That the limiting value for the sigma m SM equal to SUT, right? SUT. So that's what we call, you have what? You have the first cycle fracture, basically failure. Okay? Yeah. So the first way is that, okay, the first way of this approximation is just like this diagram here. So you basically connect these 2 points, okay, using a straight line. Okay, connect the 2 points using a straight line here. Okay. And there's a name for this guy here. Okay, this is called modified Goodman line. Okay, modified Goodman line. Okay. So remember what this line represents here. Okay, this line represents the boundary separating infinite life from what? Finite life. Okay, separating infinite life from finite life. Okay, anywhere below this line here, guess what kind of life does it have? Infinite. Anywhere beyond the line, you have finite life. Okay, yeah. So it's like those bunch of data here, right? So anywhere here it's good, and there it's finite life. Okay, yeah. So that's one way, and the other way is instead of using a straight line to approximate the data, so there's a guy called Gerber. So what he did is he used a curve. Okay, he used a curve to approximate the data here. So it's like a curve going from here to here. Okay, going from here to here. Okay. So this line here is called Gerber line. I'll give you the equation just shortly. Okay. So in the handout, I think do you have the Gerber in your handout? Yeah? Yeah. Yeah, anybody still have a handout in the back? Yeah, okay. Okay, good. So that's another way of this one here. The third one, okay, the third one is, okay, instead of connecting the SE to SUT, so they pick this SY value over here, okay, and then they create a straight line, okay, between SE and SY. Okay, so that's another way of creating this boundary. Okay, so this line here is called Soderberg line. Okay, it's called Soderberg line. Okay. Then similarly, so another guy saying is, instead of a straight line, we're gonna create a curve, okay, from here. Okay, if you can think of any other combination, unfortunately, I think I'm running out of combination here now. So that's the four basically basic failure theory for this fatigue loading with respect to fluctuating stress. So this black line here is called ASME, okay, elliptic line. Yeah, it's a curve, but still call it line here. All right. Yeah. So that's the four basic ones here. The fifth one is a special one here. The fifth one is the one guarding against the first cycle yielding. So you pick this SY on the vertical axis here, then you connect this SY and this SY together. Okay, so this line here is called yield line. Okay, it's called yield line here. So why is this line called a yield line? This is actually very easy to explain. If you pick any point on this line here, what is the value, or what is the equation for this line here? Right, for the yield line, what's the equation? It's a line, it's a straight line, right? It's a straight line. What's the straight line equation? Right now, the y-axis is sigma a, the x-axis is sigma m. So how do you represent this straight line here? Yeah, x plus y equal to sy, right? But x is this, y is this. See? So this plus this is sy. Remember what I just said at the beginning here. What shall we watch for? We shall watch for this guy here, right? We shall watch for this. So the maximum of that cyclic stress should not exceed the SYT. Okay. Well, sometimes you can, if you can avoid that, you can let it exit temporarily. Okay. Yeah. But so that's always one design criteria you can bear in mind is there is this first cycle yielding line here. So it's also called Langer line. Okay. It's also called Langer line. Okay. So that's the 5 lines at here. Okay. That's 5 lines. In terms of the line equation for each one of them, okay, the line equation for each one of them, in the handout, can I have a handout? Any additional? In terms of the line equation, okay, in your handout, the second part, okay, when you set the safety factor equal to 1. Okay, when you set the safety factor equal to 1, this is basically the line equation. Not just set it to 1, but also change those sigma a, sigma m into SA and SM. That'll be the line equation. For example, this modified this modified Goodman line, that would be what? SA over SE plus SM over SUT equal to 1. Okay, so that's the line equation. Yeah. Okay. Yeah. So just a number of comments in here. What does, again, ask the question here. How many number of cycles? If I pick a point on the line here, for example, right? If I pick a point on the line here, okay, pick a point, or here. So let's see, if I pick a point here, then according to the modified Goodman line here, how many number of cycles the part will fill? 10 to the power 6. If I pick a point over here, then according to the Gerber line, how many number of cycles will it fill? 10 to the power 6, right? Okay, so that's the meaning of this each criteria here. Okay? Yeah. So on each line, okay, every point corresponds to 10 to the power 6, okay, cycle. Okay? Yeah. Now, secondly, okay, if you look at this, if you look at the drawing at here, or look at the drawing on your paper there, right? Let's say if I have a simple question here, is the people will ask you is, can you design for, let's see, if it's required to design against, okay, both fatigue and first cycle yielding. Okay, so basically design, okay, against, okay, both fatigue and the first cycle yielding. Okay, yeah. And you're using this modified Goodman line, okay, this MG line here. Okay, so your design against both the fatigue and the first cycle yielding using MG line here. then what will be the region to satisfy this requirement? By looking at those graphs right here, what will be the region satisfy the requirement? So of course, first find this MG line here, right? And where is my first cycle line? This guy here. So if you're required to satisfy both requirements, the region must be below both, right? So then, if you look at the drawing it here, it has to be where? It has to be from here, then up to here, drawing down here. So anywhere below this one will be the region satisfying this requirement. Make sense, right? Okay. So let me finish writing here. Okay, the region satisfied requirement. Okay. So now if I extend the question slightly here, if I extend the question, so which criteria guarantee that you have this both infinite number of life and the first cycle yielding satisfied at the same time? Which one? Which criteria give you this satisfaction at both times? Soderberg, right? Because the Soderberg is below that first cycle yielding there. Okay, yeah. And then again, which one give you the most conservative result? Soderberg. Okay, yeah. So that's how you look at this bunch of lines that are here, right? Okay, good. Okay, so in terms of the usage of this line right here, I think it's pretty straightforward. Okay, so all you need to do is just those safety factors. Usually, just what you need to do right here. Okay, if you're given, so how to use that? Okay, so basically, sometimes most of the time is given a sigma A and a sigma M, and calculate the N here, a safety factor. So we're going to use F, so that's for the safety factor for fatigue loading. Okay, so calculate NF here. Okay, yeah. And in the future, shortly after midterm, when we're learning shaft design, so we're going to in shaft design, there's a very common situation. It's basically to design for the shaft diameter, right? Yeah, and the shaft, okay, in a lot of cases, basically they're going to be under this fluctuating kind of stress. Then you're basically you're going to come back here to use the equations that we introduced today, those criteria. So in that particular case, what you do is it's the other way around. It's given NF. Okay, yeah, giving NF and the loading, okay, loading condition, okay, and then you probably would do is calculate, okay, diameter, okay, D, okay, giving a shaft, okay. Now, you might wonder is how do I see the D? Where's the formula for the D? I'm going to give a summary regarding those formula for the D in the near future, right? Yeah. But today maybe we'll practice this one. Okay. Yeah. Okay. So there's nothing to say regarding this one here. The probably most sophisticated equation is the ASME elliptic line here, but other than that, it's pretty straightforward. Okay. Yeah. A couple more things I think I need to mention about this line here is, okay, those lines listed over here, okay, those lines listed over here, okay, they are for sigma n greater than 0, okay, and including equal to 0, okay, yeah. So if I set sigma equal to 0, look at all the equations that you have there. right? Look at the equations. If I set equal to 0, what will be the safety factor? Look at all the equations of the safety factor here. If you set sigma equal to 0, and what's the result for all of them? They all becomes what? Exactly. They all becomes this, right? They all becomes this. Okay? Yeah. Good. Okay, one more point added here. Okay, one more point. Now, suppose that you're not designing for infinite number of life. Okay, just like a complete reverse cycle. So that sometimes you design is just for a limited number of cycles. Okay, less than 10 to the power 6. Okay, then if you remember in that in that particular case, we derived an equation, right? Basically regarding how do you calculate the n, capital N, the number of cycles before it fails. Okay, right. In this particular case, okay, we will have similar situation at here. So let's say you decided to use modified Goodman here, okay, to calculate, to design, and then the state of stress maybe is over here, okay, maybe it's over here. So apparently it doesn't have infinite number of life, right? Okay, and then the question will be, okay, how many number of cycles, okay, the part will fail under this state of stress, basically a combination of sigma A and sigma M. Make sense, right? So that's another a similar questions that can be raised towards this combination here. So given sigma A and sigma M, okay, outside the boundary, okay, so how many number of cycles? Will it fail? Okay. Right. That's another thing that we need to look at this one here. Okay. Yeah. Okay. So this is what this is what I do here. I'll use an example to illustrate this point in here. And use an example here. So let's say we have a certain kind of loading condition in here. A steel bar and we calculate, we were given this one here, sigma max is 60 ksi and sigma mean is negative ksi. For the material SUT, it's 80 ksi. SY, okay, SYT, 65 ksi. Okay. There is this F value, which if you remember, that's called fatigue strength fraction. Okay, let's just consider it's 0.9, but it's actually a little bit smaller than 0.9, it's supposed to be. Okay, so given this loading condition, given this material, right? Let's estimate. Let's look at and let's analyze the failure of this part, okay, using a modified Goodman criteria. Okay. So let's use this modified Goodman here. Okay, we can try another one afterwards. Okay. Okay. All right. So basically, what I'm asking you is, based on the modified Goodman safety factor equation, which is this guy here. Okay, so what would be the safety factor? Okay, what would be safety factor here? So this is actually pretty straightforward. Oh, I guess I didn't give you the SE, right? So let's see, the SE is 40 KSI. So this is corrected SE. So suppose that after all the KA, KB, KC, KD is being applied, and the SE value is this. Okay. So looking at this equation, we need sigma A and sigma M. So then apply the SE as a UT. And where's the sigma A from? Sigma max and sigma mean, right? So the equation is what I showed you at the beginning of the lecture, which is this, right? Which is this. So apply the equation right here. So 60 minus 20, 80 over 2 is 40. Sigma M is 60 plus this over 2. So that's 20 KSI. Okay. Yeah. Okay. Yeah. So sigma M is greater than 0. So then very simply we substitute, okay, the values into the Goodman equation. Okay, substitute into the Goodman equation. You would get 1 over 1.25, approximately, not approximately, actually just precisely, 0.8. Okay, 0.8. So this 0.8 is less than 1, so which means the part doesn't have what? Infinite number of life, right? It doesn't have infinite life. So it will fail before 10 to the power 6 number of cycles. Okay? Yeah. So then here's a question, and I was asking here now. Okay? If it's going to fail before 10 to the power of 6 number of cycles, then how many number of cycles would it before it fails? Right? So that's the part. If I draw this, if I just roughly draw this out, and this is a modified Goodman line here, right? It's a modified Goodman line. And sigma A, sigma M, it must be outside the boundary, and here somewhere, maybe here. Okay, so that's basically the location sigma A and sigma M. Okay. If I needed to calculate the N, so recall that the way to calculate number cycle to fail when it's complete reversed stress, it's sigma A over A 1 over B, right? This formula here, and the A value is FSUT squared over SE, and B value is negative 1/3. Okay, FSUT over SE. Okay, that's B value. Okay, yeah. So this is the formula for completely reversed stress. But what we have here, it's not a completely reversed stress. It has this mean value sigma M over here, right? So we can't use this formula anymore. Okay, we cannot use this formula anymore. So what we really want is, if I still want to use this formula, I cannot use sigma A at here, right? So what we can do is, maybe we can come up with a so-called equivalent, okay, completely reversed stress. So maybe I can come up with an equivalent okay, an equivalent complete reversed stress. So then I substitute this one over here to calculate the A. Okay? Because you look at A and B, they're okay. They don't involve this sigma A there, right? They're just based on the property of the material. Okay? So it's just this guy here. So how do I come up with this equivalent complete reversed stress then? So this is basically one of the points I was mentioning here. Remember what I say, when you look at this curve here, right? When you look at this curve here, every point on this curve, theoretically, they all have the same number of cycles, which is 10 to the power of what? 6, right? Yeah. So this is how they create this infinite number of life boundary, 10 to the power of number 6. Well, I can definitely use the same analogy at here to create another boundary, which means what? I can connect this point, and then extend a point up to this axis at here. That make sense? So I can use the same analogy here. I'm going to create a line right through here. Okay? Then, if this line represent is all the point having the same number cycle to fill 10 to the power of 6, then this line here will represent what? Every point having the same number of cycle to fill, which is actually having the same number of cycle as which point? As this point here. That makes sense? Right, so suppose that, let's see, at this point, maybe it fills at 20,000 cycles. Is that okay, right? I'm not sure. We'll calculate to figure it out, okay? Suppose at this point, the part will fill at this number of cycles. So if I create a line like this, then I would have the same kind of a situation here, just like this one here, okay? Just like this. So the intersection of this line with the vertical axis, this point, okay? So the intersection of this line with this point at here, this guy here, we're going to call that what? The sigma REV that we're looking for. Okay? Because on this axis right here, your sigma M is 0. Right? Your sigma M is 0. Okay? So this point will have the same kind of damage as this point at here. Okay? That makes sense? So if you subject your parts, okay, to a combination of sigma A and sigma M, like this at here, it basically will, theoretically, will have the same kind of a damage as you subject the parts to complete reverse number cycle with the value of a sigma rev at here. Okay? Yeah. So the question is, what would be the sigma REV based on this assumption at here? It's a straight line. A straight line going through these 2 points at here, right? So the sigma REV, okay, actually it's going to satisfy, it's going to do this. So maybe come back to this line here. What is the modified Goodman line here? It's what? Sigma, not sigma, SA over SE plus SM over SUT equal to 0, right? That's this. Okay. So if you use the same kind of analogy at here, then for that particular line over there, so SE is this value, sigma REV will come here, so sigma A over sigma REV plus sigma M over SUT equal to 1. Okay, so that's the line equation, right? It's the line equation. Okay. So solving for the sigma REV, and what's that going to give us? So just want to be careful, not writing wrong here. Yeah. So sigma A over 1 minus sigma m over SUT. Okay? Yeah. So that's the equivalent completely reversed stress, okay, the amplitude of that. Do we have a sigma A, sigma A? Yes, we do, right? Do we have a SUT? Yes, we do. So this value can be calculated, which is 53.3. Okay. Okay. So once we have this guy now, we can replace this sigma A with this sigma ReV to calculate number of stress for it to field. So N is sigma ReV and over A and 1 over B. So A and B can be calculated based on the SUT and SE value, right? Yeah. So altogether, okay, substitute all the values into it. Your N is 3.4 and 10 to the power 4 cycles. Okay. Okay. So if you use the same analogy here, said, okay, what about if we use a different criteria? Let's say, what if you use Gerber lines, right? So basically, what if you use this Gerber line in here, right? So basically, what you do is you create a curve, okay, which passing through that point and connect the SUT and then intersect at the vertical axis, right? Yeah. So if you use the Gerber lines, then your sigma ReV, okay, will slightly different now. Okay, this is your sigma ReV using Gerber line. Okay. So then you calculate your N based on that formula. Now before we calculate, take some quantitative kind of a view here. So here's a Gerber, here's a modified Goodman, and you're trying to calculate an equivalent sigma ReV. One is using sort of analogy to the Gerber, the other using analogy to the Gerber line, the other one using the analogy to the Goodman line. So which one do you think will yield a larger number of cycle to fill? Well, see this number, this is N, the results from the Gerber, right? If I use this Gerber, this is the results from Goodman here. If I use Gerber, so what do you think of this N here? Would it be bigger than this or smaller than this? So basically the answer is here, right? Because the Gerber is on the top of here. Gerber is on top of the Goodman here. And you have a state of stress sigma A and sigma M. So actually chances are what? Chances are if your state of stress is within the two, so according to Goodman it's limited number of cycles. But according to the Gerber it's actually what? Still infinite, right? So basically if I calculate this number, that number is supposed to be greater than this one here. Okay? Yeah. So the results prove itself. Pretty close to 10 to the power 6, right? Pretty close. So that basically tells you the Goodman is a bit of a conservative at here. Okay? It's a bit of conservative. Okay? Any questions? So I had one of these kind of example in assignments, and I had one of these example in the last year midterm. You know, basically calculation of this failure, right? Yeah, for fluctuating kind of stress. And oh yeah, by the way, I think a midterm is approaching pretty fast. What is our midterm? It's next week, right? Yeah, so let's just confirm here. I'll email you guys. February 13th. So it's next week. So I generally wanted to finish that before the break. But that's not before the break, eh? Well, the break is over here. Okay. But anyway. Well, any questions regarding this date is okay? Yeah? Okay. Yeah. Yeah, I'll talk a little about details. So you can bring a double-sided. It doesn't matter, formula sheet. But it's the midterm. I generally don't. It's not an open book. Okay. So you can bring the formula sheet. You can bring the handouts that give it to you today's and in other lectures. Those graphical things, the failure one. Those you can bring. Okay. Yeah.
And we can make our own formula sheets.
You can make your own formula sheets. Yeah. Okay. Yeah. So any formula is fine, right? As long as you don't include examples in the formula sheets. Okay? Yeah.
And any values we need would be given on the test, right?
Huh?
Values we need from the textbook would be given on the test.
Yeah,
right?
that's right. Yeah. So you might concern is what about the K, KB, KC, KD things, right? I will give you enough information if you are required to look up for those things there. Okay. For example, I'll give you a table maybe attached in the question, so you can look at the table to find the values. Okay. Yeah. If there's any stress concentration factors that you need to use, sometimes I just tell you in the question to simplify the calculation, the process. Okay. So more important is you need to understand the process to do the calculation. Okay. And least concerns about looking up tables. So in a final exam, okay, actually in your design project, you can have lots of exercise of looking up tables. Okay. Yeah. Okay. So that's that for calculating number of cycles. So what's my bullet points here? 3. Okay. Number 4. Okay. For number 4, I'll skip one part of it here. So for number 4, actually, I don't think I should skip here. For number 4 is what if my loading is a fluctuating torsional kind of stress? Okay, so fluctuating torsional stress. Essentially, what we're dealing with tau A, tau m, or maybe tau max and tau mean, right? That's fluctuating torsional stress. So no need to rederive everything. So all you need to do is just do a few replacement steps following here. Okay. First of all, so what you do is your sigma A is replaced with tau A. Your sigma m is going to replace with tau m. Okay. Yeah. So you have those design equations, those safety factor design equation, right? So replace the sigma A, sigma m with tau A and tau m. And then, okay, when calculating SE, now remember, when you calculate the SE, there is this KC loading factor. The loading factor needs to be applied, okay, at 0.59. Okay, yeah, so when you calculate SE, set this KC to 0.59. Okay. For the SUT, for some of the design equation, you have SUT, right? So SUT needs to be changed to SSU. So SUT is the ultimate tensile strength. So now you're dealing with torsional stress. So we need this ultimate shear strength. The ultimate shear strength is approximated to be 0.67 SUT. Okay. So the SUT needs to be changed to this SSU. And for some equation, they don't use SUT, they use SY. For example, the Soderberg, right? They use SY. Then the SY also has to change SSY. So that's the shear yielding strength. And this one is approximately 0.577 SYT. Okay? Yeah. So those are basically a few replacements that you need to conduct before you apply. For example, the modified Goodman, right, the mg line, okay, becomes, okay, so tau a over se and tau m over ssu, okay, equal to 1 over nf safety factor. Okay, safety factor. Okay, so that's the replacement. Okay, it's very simple. Bullet point 5, stress concentration. So how do we apply the fatigue stress, okay, concentration, okay, factor? So you might think this is kind of unnecessary because, you know, in the previous lecture we talked about, you know, we may have Kf, we maybe have a Kfs, right? Maybe have a Kfs. Okay. So then, if you have a nominal value, then you basically apply the Kf in front of the nominal value. But in this case, we're not just having sigma a. So we also have sigma a and sigma m. So basically, when you apply this fatigue stress concentration factor, you're really applying to the Kfs to two nominal values. One is this sigma a nominal, the other is a sigma m nominal. Okay, yeah. Is that okay? Yeah. So when you calculate sigma a and sigma m, so that's what you do. So this is going to be your sigma a, and this is going to be your sigma m. Then you substitute these two into the modified Goodman line. That's basically sigma a over se, for example, if you use mg lines. Okay. So that's where you substitute, right? This over here. So if it's a torsional kind of a fluctuating stress, so same thing. So tau a will be the Kfs, okay, tau a naught, okay, tau m will be Kfs, tau m naught, okay, tau m naught, nominal. Okay. So this is what we use. Okay, what I would suggest that we all gonna stick to this way. Okay, it doesn't matter what. We're gonna basically apply this Kf to both of these nominal values that are here, and then substitute into the design equation. Okay, so this way here, there's a meaning actually. When you do this, you're designing, okay, not just to prevent this fatigue failure, but also you're trying to prevent local yielding here. Okay, yeah, local yielding. So in the textbook, there's one short section there is actually discussing about how the Kf should be properly applied. There's another way, basically, instead of apply the Kf to the sigma naught, sigma m naught here, so they only apply the Kf to the sigma a, but this one here just set it to 1. Right? So this one here just set it to 1. That's another way of applying there. But if you apply it in that particular fashion, it basically means the local yielding is not preventable. Okay, so it's inevitable. Then we only apply the safety factors to the sigma a. We're basically only designing against the fatigue failure. Okay, the fatigue part. Okay, stress. Okay, yeah, because sigma m, of course, is associated with the steady one, and sigma a associated with the oscillating, the cyclic component, alternating component, right? Yeah. Okay. So this is what we apply here. Okay. Yeah. Okay, a lot of small knowledge points that are here. Okay. So we have a couple minutes here. I don't think I'm gonna finish now, but we'll start it here. This is actually after all the talking here, this is probably the most important part, which is called combination. The most general type of loading. So combination of loading. Okay, combination. So what's a combination, right? This is probably kind of can be explained by itself. In the previous example, you know, this one here, that's when you have pure torsional kind of fluctuating, right? And then this one here, that's when you have pure normal stress, tensile stress kind of fluctuate kind of stress. Okay, yeah. So then the question is, what if what if we have it's a combination? Basically, there exists the sigma A. Maybe the sigma A comes from bending. Maybe there is the sigma M. Okay, also come from bending. Okay, and there might be from a tau A, which is probably torsion. Okay, and there probably a tau M. Let's see, maybe also from a torsion. So basically, the stress, right, comes from different source. So some contributed from the torsion, some are contributed from a bending moment, or maybe axial loading, right, normal stress. So you have, okay, both the sigma and the tau, okay, contributing to this loading here. That's what we call the combinations of the loading modes at here. Combination, right? Yeah. So this is where I'll bring up that example that I substituted there. So let's say I have a shaft here, right? And then you have this F loading on the top of the shaft. Okay, yeah. Then the shaft is rotating. Let's see, at omega, okay, constant velocity. And at the same time, you have a constant T, okay, subject added to the shaft. Okay, so both F and T are constant. Okay, constant. Okay, so now if I cut a cross section, okay, if I cut a cross section, then I'm gonna look at, okay, I'm gonna look at a location A, the change of the stress at the location A. So location is rotating as the shaft is rotating, right? Yeah. So what will be the stress component? Right? If you draw a diagram basically later, what will be the stress component, or what will be the stress contribution for the location A or any other location? That makes sense? Okay? Yeah. So if I don't have the torque here, if just the F here, then the A will experience basically a completely reversed what? Stress, right? Completely reversed stress. And in this particular case, it's a sigma A. So then sigma A is not 0. Sigma M is what? F is constant. And sigma M is 0. Okay? So that's when T is 0. So now you have the torsion T added on it. The T. And T is a constant. So basically, the tau A, if I talk about tau A, tau M, what would be the tau A value? T is 0. If T is, if T is a constant. If T is a constant, what does it cause? It's going to cause what? A constant torsional shear stress, right? So this one here, you would call that tau M. So basically, tau A will be 0, and this is not going to be 0. Okay. So now you see, in this particular case, it is actually a very common situation. You have a sigma M. You have a sigma A not 0 and tau A not tau M not 0, and then these two are 0, right? So you have a combination of a sigma and a tau added here. Okay, not just a pure sigma or not just a pure tau. Was that okay? Yeah. So the question is, how do we design or analyze when we have this kind of combination of loading modes? Okay, yeah. So if I said I'm still gonna try to use those design equations, those design equations over here. Okay, I still want to use those design equations. Maybe I still want to use the modified Goodman line, okay, to design. So then, if I still want to use this, where's the modified Goodman line? Well, modified Goodman line, it's this guy here, right? It's this guy. Okay. If I still want to use, then I can't just simply use sigma A and sigma M anymore, right? Because that's when you only have sigma A, sigma M. So we had to change this guy here. Okay, we're gonna have to change this. Okay. So let me write it down here. So if I still want to use that line here, that modify Goodman, so then we're not going to call the sigma A anymore. So we're going to call the sigma A prime and sigma M prime at here. So I'll tell you what sigma A prime and sigma M prime is. Okay. Yeah. So sigma A prime, sigma M prime are the von Mises stress, equivalent von Mises stress. All right. Yeah. So sigma A prime, where's sigma A prime? Sigma A prime is from all the A component. So it's from sigma A, maybe you have a bending contributing sigma A. Maybe you have a torsion, not a torsion. Maybe you have an axial contributing sigma A. And maybe you have a tau A, which is torsion contributing tau A. So those are all the alternating components here, right? Those are the alternating components. So we're going to calculate the von Mises stress based on this A component at here. That makes sense? Okay. So the sigma M is going to be calculated based on all the M components. Okay, or the M components. Okay, so what's the equation then? The equation is basically the von Mises stress equation. Okay, so here is the equation. I'll put down the equation in here. Okay, yeah. So sigma A prime. Okay, it's a little bit long equation in here. Okay, and I'll change this one here because we need a general equation. So what we do is we're gonna multiply each one of the component here, which basically includes the fatigue stress concentration factor. Okay, maybe it's 1, but maybe not. But we're gonna include that at here. So first, Kf, okay, sigma A due to bending, okay, plus Kf axial by sigma A axial over 0.85 squared, okay, and plus 3, okay, Kfs torsion, okay, tau A, okay, torsion square over 1/2, okay, 1/2. So remember, what was the von Mises stress? Von Mises stress is sigma prime equal to what? Sigma x squared minus sigma x sigma y squared plus sigma y squared plus 3 tau xy squared, right? That's von Mises stress formula. Recall that, right? That's von Mises. So right now, okay, what you have here is the way to calculate this one here. It's as if this. You have a, let's say if you have a stress element, okay, if you have a stress element here, okay. So we're dealing with basically most of the 2D planar stress. So then there are two components that are here. One component is this Kf axial, sigma A axial, right, due to the axial loading. And the other one is Kf bending. Yeah, I missed the bending here. The Kf bending. And then sigma A bending. Okay? Yeah. And at the same time, you might have a shear stress, okay, due to the torsion. So this one is the tau A and due to the torsion. Okay, and then multiply by Kfs here, torsion. Okay, so the two addition at here, give you that sigma x. So planar case, if the planar state of stress, then sigma y will be 0. Okay, and so then basically there's only one component here, either sigma x squared or sigma y squared. Okay, and you have 3 tau x y squared for sure over there, right? Yeah. Okay, so that's basically where this formula from. But you might argue there's one simple argument in this. Why are you dividing 0.85 at here? Right? You see that? Because I'm not directly adding these two, right? I'm not directly adding these two. I'm actually, the formula actually divided by 0.5 for the sigma A axial. Okay? So keep that as a question mark, and I'll explain that in the next lecture. Okay? Yeah. All good? Yes.
Which lecture's the cutoff for the lecture material?
I think it will be today's lecture will be good. So, because next lecture, let me just see. Yeah, next one we're going to talk about gear now, right? Yeah, I think today's lecture will be the cutoff.
Okay.
So, including today's. I'll send an email.
Alright, thank you.
I just had a question about the formula for the von Mises stress that was up there.
Yeah.
Because it said that it's the stress in the x direction minus the stress in the x minus, or times stress in the y squared.
Yeah.
Wouldn't that term have a different...
So,
oh, that's all squared.
yeah, you see.
Sigma x, sigma y all, like, is that all squared, or is that just the sigma y squared? Just the second.
Oh, sorry. What? There's no square here.
There's no square.
Yeah, there's
no square. Okay.
Yeah.
Yeah, I was wondering about that.
Yeah.
I just have a question about